Non-homogeneous differential equations. A second order linear non-homogeneous differential equation is in this form. Second order in the sense y double prime, and linear means look at these functions g, q and p. They are functions of independent variable t. And non-homogeneous in the sense this is a non-zero function. Okay, this is not a zero. And we call, if we make this zero, then we call the associated homogeneous differential equation to 1. And the theory we are about to develop works for any function like p and q. But our problems in this course, we mainly work on constants, okay, numbers here. And we can have some functions here, non-zero function, but we can always divide through by that. Okay, here is a theorem, and we already know how to solve this homogeneous equation. So in this section we are trying to solve this non-homogeneous, and when p and q are numbers, then we find the characteristic equation, and depending on the roots, we had 3 cases: distinct real and distinct roots, equal roots and complex conjugates. Okay, using that, now we're going to solve these non-homogeneous equations. So here is a theorem. Suppose that uppercase y1 and y2 are 2 solutions to 1, okay, for this non-homogeneous, and little y1 and y2 are a fundamental set of solutions to the associated homogeneous differential equation 2. So we got y1, y2, 2 solutions of 1, and little y1, y2 are a fundamental set of solutions. So fundamental set of solutions means they are solutions and they are linearly independent. Okay, in that case, if we find the difference of y1 and y2, y1 minus y2, that is also a solution of 2. That is a solution of 2, and this solution can be written as a linear combination of y1 and y2. I mean, that we already know. In fact, when we have a solution of this, then any solution of this homogeneous equation is a linear combination of y1 and y2. As long as y1 and y2 are a fundamental set of solutions, I mean, this part is kind of clear. Now we need to show y1 minus y2 is a solution of 2, where y1 and y2 are coming from 1. So let me prove this. So here is the proof. So y1 is a solution, y2 is a solution of 1, means we can replace little y by y1 and we still get right hand side, and we replace y by y2, we still get right hand side. Okay, note that y1 double prime plus pt y1 prime plus qt y1 equals g, because y1 is a solution. Similarly, y2 is a solution, so this is true. Now we are trying to show the difference is a solution to 2. Equation 2 means when we replace little y by this difference, we have to get 0. Now, so what is equation 2? Y double prime. So here is y1 minus y2 double prime plus pt y. In place of y, we are writing this difference y1 minus y2 y prime, that's y prime by the way, plus qt, y is y1 minus y2. So if this happens to be 0, if this is 0, then we can say y1 minus y2 is a solution to homogeneous equation 2. So let's simplify this. So this second derivative is distributive here, y1 double prime minus y2 double prime, same thing here, and when we distribute this and collect, we get this y1 double prime plus pt y1 prime plus qt y1, and we got more here about y2, so I can subtract minus, this is 1, this minus sign. Now y2 double prime here is negative, but if I factor negative, it's going to be plus pt y2 prime plus, is a negative but we factor out qt y2, just y2. So this can be simplified to this. Now y1 is a solution, so this is gonna go to gt, so this part is gt minus y2 is also solution of 1, so look at here, this is also gt, so that is 0. So we replaced this y by y1 minus y2 and we got 0. That means y1 minus y2 is a solution to equation 2. Okay, that's the first part. And since little y1 and y2 forms a fundamental set of solutions to equation 2, then any solution of this equation is a linear combination of y1 and y2. That means any solution, this is one solution now, this can be written as c1 y1 plus c2 y2. The second part is kind of obvious. Okay, now any solution, now we got y1 minus y2 is c1 y1 plus c2 y2 as y1 y2 forms a fundamental set of solutions. Okay, now why we care about this thing, because now we can use this theorem to write down the general form of the solution to 1. You know, 1 means our non-homogeneous here. Okay, we are trying to solve this non-homogeneous system. Now using that theorem we can write down the solution. So let's suppose that little y is a general solution of 1 and yp is any solution to 1. Okay, I'm just trying to say this one is like y1, uppercase y1, and yp is like y2, y1 y2, it's like that. Then using the second part of our theorem, like this one, this y1 minus y2 means now little y minus yp is equal to c1 y1 plus c2 y2. Okay, we can write this using this one, where y1 and y2 are a fundamental set of solutions. Then now we can just move this over, add yp, so we get y little y is c1 y1 plus c2 y2 plus ypt. Okay, so this one gives us the general solution to a differential equation. Okay, the very first one, equation 1, is we can say, oh, this is just a complementary solution, and we can write yc, and that is any solution, that's yp. So the general solution of non-homogeneous differential equation is just a sum of two solutions. We got yc, it's complementary solution, this is coming from the homogeneous equation, and yp is any solution of 1, okay, and it's called a particular solution.